Okay, so this is the way you do mathematics. You're trying to figure out, well, what's the relationship between the soup of intersections and unions and the individual sets? Yes?
Your minimum maximum of the set, is that just saying whichever one is greater or whichever one is least?
Yes, because that was what we discussed right here. Okay, so, right, so this is saying, I mean, to sort through what this is saying that you look at these two things, whichever one is smallest, if this is true, whichever one is smallest, it's equal to that. And for this one, if this is true, then you look at these two and pick out the biggest one, because, you know, I could swap the labels A and B, and in that case, the ordering of these would change, right? So that's why I replaced, you know, in this picture, it looks like soup of A intersect B equals soup A, right? In this picture. But that's just because we happen to label this one A. If we reverse the labeling, the picture stays exactly the same, and A intersect B is exactly the same thing. But then, you know, so what matters here is not that it's called A. Yeah, sometimes it matters what something is called, right? But in this case, what matters is not that it's called A. What matters is that if you look at these two things here, then in our picture anyway, this is equal to the smaller of the two. And so that's why instead of writing this down, which you already know is not going to be true because you swap A and B and it's not true, okay? That's why instead of putting just soup A here, we put the minimum, which captures the real idea, which is that it's the smaller of the two. Okay? All right, let's look at the first one. So now this is something you need to get used to. Often when you're showing that things are equal, especially when you're doing real analysis, right, you want to show one is less than or equal to the other and then show the opposite inequality. Okay? So we're going to start with this one. This is just like, and it's actually logically sort of equivalent to showing an if and only if statement, right? Okay? So let's look at this. Now, this one should be fairly quick. Okay, because look at the lemma up here. The lemma up here says that if one set is contained in the other, then the soup of this inside set is less than or equal to the soup of the set that contains it. Now, what do we know about the relationship between the intersection of A? So just note, what's the relationship between the intersection of A and B and A? Yeah, this is one of the first things that you ever proved in here, right? About sets. So by the lemma, what do we know?
Soup A intersect B is less than or equal to soup.
Okay? And similarly,
it's less than or equal to soup B?
yep. Okay, so what have we got? We got this thing is less than or equal to that, and this is also less than or equal to the other one. So whichever one is the minimum, it's less than or equal to both of them. Okay, so this is equivalent to showing something's less than or equal to a minimum, right? If you show it's less than or equal to both, then you got the minimum in there somewhere. So, you know, you could work harder with this and say, well, let's suppose that soup B is less than or equal to soup A. And then you could do this argument for that one, right? Okay, but that would work. Okay, and then you wouldn't have a similarly there, but, you know, there are various ways to do this, but this is maybe the simplest one. So this tells us that soup of A intersect B is less than or equal to the minimum of soup A and soup B because it's less than or equal to both of them. So whichever one is the minimum, you got it, right? Questions about that direction? Okay, let's think about the other one, right? So the other direction would be, and I'll write it out actually, would be that the sup of A intersect B is bigger than or equal to the minimum of sup A and sup B. Okay, so now right away you should start realizing that you're running into a bit of trouble here. Okay, what's the easy inequality to prove about a sup? What's the thing that's easy to do that I mentioned earlier? Which direction? Sup bigger than or equal to something or sup less than or equal to something? Yeah, if you're trying to prove sup less than or equal to something, what do you have to show about that something?
Upper bound.
It's an upper bound. Done. Right? This, okay, what do you got there? Well, one thing you can do is show that the sup of this set is actually an upper bound of a set, and then when you get things in the set, then okay, those things are, right, bigger than or equal to, or less than or equal to, sorry, the sup of that thing. Okay, so this sounds complicated. There's a good reason, because this isn't going to work. Okay, and the reason it's not going to work is that, again, if you want to show the sup is bigger than or equal to something, those somethings, really the only way to do it is eventually to have, well, there are other ways, but to have those somethings in the set. And are these going to be in A and B? Necessarily? No. If they were at A and B, what would we call them? Max. So you might think, okay, I could do something if this were just a max. Okay, maybe. Okay, because then at least you'd have them in sets and so on, right? But then what? Then it still has to be in the intersection, and well, maybe not. Okay, and in fact, this is not true. Okay, so the only thing we can get out of this is this direction. Okay, so this is false. Now, you all know what I keep telling you, and I had to drag it out of what I think it was Trevor, or right up here, or one of you guys, right? Long counter proof of a statement is false, but I said usually what you need to do is you need to come up with a counter example, right? That's usually the easiest thing to do. Just pick up some concrete thing and say, look, this is not true. Okay, well, there you go. That's your homework. Okay, it's one of your exercises. You don't need to write down because it's in the text, right? But you'll be checking that. Okay, you'll be finding a counter example. Now, let's look at what went wrong. I mean, here we have this picture, right? This picture's great. We got our picture, and look, there it is, right? So what's the problem? I mean, you know, according to the picture, it's a true statement. Well, I mean, there's one general thing that's wrong, right? And that is that, well, the picture is not representative of what can happen, right? So the picture is too easy, too simple, right? This is why I keep telling you, you've got to be careful about pictures. They can help you, they can hurt you, right? And the reason why it seems to work, you can say, well, wait a minute, I can do anything I want with A and B. Slide them back and forth, yes?
Is it because the sup of A could not be contained in A, but the sup of AB A intersect B could be contained in A intersect B?
Let's see, I think that should work if I understood all that correctly, but it's a little, the example is easier than that. Okay? And I won't get into it much because I don't want to give away your homework, right? Because it is your homework to come up with that. But the hint is to actually just use two sets, each of which has two numbers in it. And you'll see once you get the example why an interval is not the way to do it. Basically, the problem with an interval is it includes everything in between the inf and the sup. And in fact, this is, that's actually how we'll define those later. So if you're drawing things as intervals, you'll get into trouble. Okay, in some cases, because sets can be really bad and ugly, right? And they don't just line up like little bars like that. Okay. So then what about this one? Well, of course, it would be easy if it were just like, greater than or equal to or something like that, okay? But no, this one is equal, and this is one of your homework exercises to prove it's equal. Okay? And you say, oh, but the hard part here was the other inequality. Well, yeah, you're going to have to think about that, right? Okay, but it actually works in this case. It's not very difficult to prove. Okay, so the other inequality here is impossible. This is not true. And here it's not so bad. Now, the next theorem gets us into using epsilons. I know you had a little exercise with an epsilon in there. That was just to get you warmed up. And now we're going to come into epsilon sort of full tilt, just like you had to do in calculus. The problem with calculus is that when you used epsilons like in continuity. Does anybody remember what you actually did with epsilons? Well, okay, so there's my point. Okay, so right, and what you did with them really is that you basically got the definition. If you still got the delta epsilon definition of something like continuity, what you did was then you did a whole bunch of exercises. Here's your delta, find your epsilon. Okay, and so in your mind, so you're nodding, right? Oh yeah, now I remember what we did, right? But do you actually remember the definition and have any sense for what it means, right? And the answer is no, because in calculus, you've been trained to think about the exercises that you have to do. And then it becomes, yeah, if I handed you this thing and I said, here's delta, find epsilon, you could probably do that. But on the other hand, you wouldn't really know what continuity meant, because it became just an exercise and you learned how to do that exercise and you didn't learn to actually understand anything. Okay? And this course is where you start to learn to understand mathematics. And even if you're not going to be a math major, if you're going into engineering or business or something else, if you can understand it, that puts you a cut above all those people who can't. And believe me, there are a lot of people, or don't. I shouldn't say can't, don't. Have never learned to actually understand the mathematics. Because then you can do new things. Whereas somebody who doesn't actually understand it can just do what, kind of like a computer, right? You can just do what you've been told how to do it. And if you don't understand it, you can't do anything new. And believe me, if you're working for a bank that's trying to maximize its investments, they want you to find something new that works that nobody else knows about yet, because it only works so long as nobody else knows about it. So there's a lot of value in understanding things so you can do new things that other people aren't doing. Okay? And people will pay you a lot of money to do that, unless you're a math professor. But hey, that's life, right? Okay. So, but yeah. So again, it's important for everybody, if you want to really, do new and interesting things in your field, to understand the mathematics behind it. So that brings us to the approximation property. Now, the way I'm going to introduce this is I'm going to try to get you a sense for the intuitive idea behind this. And the intuitive idea will make absolutely perfect sense, I hope, right? But as usual, when you're doing mathematics, your intuitive idea is useful, and it can help you decide whether something's true or not, but, and I'm not going to say at the end of the day, because I hate it when people say that over and over and over again, right? Okay, but you must actually prove what you're doing, right? Because your intuition can lead you astray. Right? So intuition is useful, but it's not the last word. So let's think now. Let me just draw a picture over here. And so here's R, right? And I'm going to make A. I'm not going to make it an interval, right? Just to not get you going down that path. Okay? So here's my A. And let's suppose this is the sup of A. Okay, so we already have S1, right? Now, I'll tell you what, I'm going to erase all this and I'll put them side by side. That'll be a little easier. I'm going to introduce two new conditions. I'm going to introduce A1 and A2. And A1 is just that S is an upper bound of A. And you observe right away
Same as S1.
it's the same as S1. So why am I doing this? Well, you'll see, okay? So these two are the same, so nothing interesting, okay? So this is my S. Now, S2 says that if I take any upper bound of A, then S is less than or equal to M. Yes. Okay, so that says, well, the picture is that if I pick up any M, then that's less than or equal to S. The problem is that this M is kind of very far removed from A. And so if you're trying to show something involving A, it can be difficult sometimes to show this. So I'm going to flip the picture around a little bit. And I'm going to say, let's suppose that there's a gap in here and there are no points in A in there. Okay, so let's suppose I can back up a little bit and there's nothing in A that's in there. What does that tell you about this thing? No, this curved, this point right there. If I can go back a little bit and there's no A's in there anywhere, what does that tell me about this new point here where I've backed up? What is it, actually?
It's another upper bound.
It's an upper bound, right? Because all of A is to the left of it. And is that a problem? Yes, because S is supposed to be the soup. And so all the upper bounds are supposed to be over here. Okay? So what this is saying is that if I back over to the left at all, and backing to the